Correlation coefficient tells you one thing. It tells you how linear is the data. Let's look at an example. Here is Anscombe's data set number 1. If we graph it, it looks kind of like that. Looks like it's relatively linear, right? But correlation coefficient quantifies that. Here's the equation. What we'll do is we'll just run through how to actually calculate it, and then we'll talk about what this equation is really doing. So, to begin with, we have our x bar, y bar, our means, sample standard deviations of x and y, and we can get all of that from two var stats, right? L1, L2, gives us all that information. All we have to do is plug it in, and we get, x bar, y bar, sample standard deviations, and all plugged in. Now, what x sub I, yi refer to is the fact that you have to do this for each and every point. So we can do that in this table, and what we have, what I would do would be to do this in my stat lists. This big capital sigma, of course, says to add up all of these, which is 8.162. And 1/10, and we get our correlation coefficient of 0.816. Now, what's this big nasty equation really doing? Well, we have to look at this piece by piece. First of all, x bar. We're going to look at this particular point as an example. All right. We're going to graph x bar, which is 9. All right. And so here's 9. So if we talk about xi minus x bar, well, that's just a difference. That's that distance between the point and x bar, and we're going to do that for every single point. Right? Now, we do divide by the sample standard deviation, so that distance is really not the absolute distance, but the distance, it's the number of sample standard deviations this point is from your sample or your x bar. Now, I minus y bar, it's just the same thing in the y direction. This creates a rectangle. So really this is like the width. This is like the length of that rectangle. We're multiplying them together, and that of course gives you area. So really these numbers are areas of rectangles. And we can do that for another point down here. And they're all just areas. Notice that even though this is below the x bar, y bar, it's still a positive area because both of these terms will be negative. Two negatives multiplied together give you a positive. So what we're going to do now, I need to clear some space. Let's talk about what you do with the correlation coefficient. Once you have it, you use it to interpret your data. Right? There are three ways that you interpret your data. You have strength, direction, and form. Strength is just looking at the number. Right? And these boundaries, they're just guidelines. Right? There's nothing really magical about 0.8. If it was 0.79, I might still call it strong. Right? These are just guidelines. So, for example, this 0.816, I would say is strong correlation. You can see that the correlation coefficient runs between -1 and +1. Positive being direction, right? This is positive slope, right? So it's got a positive correlation coefficient. If we had data that went this way, that would have a negative correlation coefficient. If we look at this one, I would call that strong. We just talked about positive versus negative, so it's definitely positive. Form is a little interesting. We said in the beginning that it looks, pretty linear, and that's accurate. There are curved and clustered. Let's look at some examples of form. So here's our linear, right? Nice, seemingly straight line. Now, clustered, you can see that there are kind of groups Right? And you can do a linear regression, a linear model, but it's telling you that the actual behavior of the data isn't really spread out evenly on that line, right? Which is important information to know. It tells you that the behavior of the data is not exactly the same as the behavior of a straight line, although you could model it with a line. Similar to curved, I mean, you can throw in a linear model, and it could even have a pretty decent correlation coefficient. But again, it doesn't exactly match behavior, right? Form is about behavior. So let's get some examples of the different strengths of correlation. So we go from -1 to +1. 0 is no correlation. All right, there's no way you could actually fit a line through here. Would the line go this way or this way? Who knows? 0.3 is really difficult to determine. There's maybe slight negative correlation. 0.5, now they're kind of alternating between positive and negative just to give you some practice. It's starting to have some recognizable correlation. 0.7, right? This is where you start really recognizing that there is, a linear relationship here. And certainly by 0.9, it's pretty strong, and 0.99, of course, it's very strong. 1 or -1 is perfect. It would be perfectly lined up. Let's look at how to do this on the T84 calculator. Here's our calculator. I believe, let's just check that I plugged in our data. Yes, it's there. So I want to show you where to find R, or correlation coefficient. And I'm going to do this twice. The first time it's not going to work because I need to show you what you have to turn on. So we go to Edit, or Stat rather, Calc, and if we go down, I believe it's the 8th one, we have linreg. There are actually 2 linregs, you can see. This is the statistics way of doing it, A plus BX. This is more the algebra way of doing it, AX plus B. We're in statistics, so let's use that. We have X and Y, that's all fine. Let's just calculate. This is doing the linear regression. It's getting us the equation. And it doesn't give us the correlation coefficient yet. What we need to do, and this is in the catalog, which is down here, second 0. We need to turn the diagnostics on. And if we go alpha D, it should bring us to the D section of the catalog, or maybe not. All right, there we are. And if you scroll down, we should be able to find some way. There we are, diagnostics off, and there's diagnostics on. We have to hit enter. Now we have to hit enter again to actually run the diagnostics on. It's done. Now what we can do is go back, do our linreg, just like we did before. Only now, with those diagnostics on, it gives us not just A and B, but gives us R squared. We'll talk about that in a little while. That's coefficient determination. And R, which is our 0.816, just like we did by hand.